Gravity assist maneuvers, often called gravitational slingshots, are key to exploring the vast distances of our solar system without burning excessive fuel. By leveraging a planet's or moon's gravity, a spacecraft can alter its speed and trajectory without significant propulsion, hitching a ride on celestial forces. For example, the Voyager missions used gravity assists from multiple planets to gain the speed necessary to journey to the outer edges of the solar system. Imagine a spacecraft approaching a planet. As it gets closer, it falls into the planet's gravitational field, gaining speed along the way. The spacecraft then whips around the planet, leaving with a new speed and direction, which depend on the gravitational influence of the planet and the spacecraft's trajectory. The outcome depends on the planet's motion relative to the spacecraft. Passing behind a moving planet can give the craft a speed boost, while passing in front can help slow it down. This technique allows spacecraft to travel further and faster with much less fuel than would otherwise be required. It's the interplanetary equivalent of a skateboarder catching momentum by pushing off a moving car, which involves precise timing and control, just as gravity assists require exact calculations to avoid potential collisions or incorrect trajectories. Gravity assists are not just theoretical. They have enabled some of the most ambitious missions in the history of space exploration. For instance, the Voyager missions, launched in 1977, used gravity assists to travel from one planet to the next, all the way to the edge of our solar system and beyond. Without these gravitational slingshots, the Voyagers wouldn't have had enough speed to complete their grand tours. The Cassini mission to Saturn utilized gravity assists from Venus, Earth, and Jupiter to conserve fuel and reach Saturn. These slingshots were critical to the mission's ability to explore Saturn and its moons in detail. The Parker Solar Probe, to get closer to the Sun than any previous mission, performed multiple flybys of Venus, gradually decreasing its distance from the Sun. Each flyby brought it closer, allowing it to study the solar corona in unprecedented detail. On a grander scale, the concept of gravity assist is part of the Interplanetary Transport Network, ITN, a web of low-energy pathways through the solar system. These routes take advantage of the gravitational forces between planets and moons, allowing spacecraft to move vast distances with minimal energy. These routes are often referred to as gravitational highways. The trade-off, however, is that traveling along these pathways can take a lot of time, as they often involve complex, indirect trajectories. Nevertheless, these longer travel times can be advantageous due to reduced fuel costs and the opportunity to explore different regions of space along the way. Recently, the European Space Agency's Jupiter Icy Moons Explorer, JUICE, performed a daring maneuver by utilizing both the Moon and Earth in quick succession for a gravity assist on its way to Jupiter. This double assist showcased the creative ways engineers are using gravity to navigate the solar system. Gravity assists aren't just a clever trick. They're essential for modern space exploration, especially given the increasing interest in long-term missions to the outer solar system and even interstellar exploration. With current propulsion technology, many deep space missions simply wouldn't be possible without these slingshot maneuvers. They allow us to send probes to the outer reaches of the solar system and beyond without building spacecraft the size of skyscrapers to carry all the required fuel. Gravity assist networks truly embody the spirit of ingenuity in space exploration, helping us navigate the solar system for almost free. While gravity assists save significant fuel, there are still costs involved in mission planning, precision adjustments, and ensuring accurate trajectory calculations. If you enjoyed this deep dive into the mechanics and history of gravity assist maneuvers, don't forget to like, share, and subscribe for more insights into the engineering marvels that make space exploration possible.
Nuclear thermal rockets, NTRs, are once again capturing the attention of scientists and space exploration enthusiasts. With their potential to vastly outperform chemical rockets in terms of efficiency, NTRs could be a game changer for future deep space missions. But what makes them so special, and why are we considering these powerful propulsion systems now? Unlike traditional chemical rockets, which burn fuel to generate thrust, NTRs utilize nuclear fission to heat a propellant, usually liquid hydrogen. The hydrogen is then expelled at very high speeds through a nozzle, producing thrust. The key advantage here is the specific impulse, which measures how efficiently a rocket uses its fuel. Higher specific impulse means greater efficiency, allowing the rocket to produce thrust for a longer duration using the same amount of fuel. NTRs could provide twice or even 3 times the specific impulse of chemical rockets, allowing for faster travel times and reduced propellant needs. One of the main challenges of human missions to Mars and beyond is the amount of fuel required and the duration of the journey. With NTRs, a round-trip mission to Mars could be significantly shortened, from approximately 18 months total with chemical rockets to about 8–12 months with NTRs, reducing the risks associated with prolonged exposure to cosmic radiation and microgravity for astronauts. A shorter journey also means fewer supplies and logistical requirements, making deep space missions more feasible. Nuclear rocket research began in earnest in the 1950s and 60s with programs like NERVA, Nuclear Engine for Rocket Vehicle Application. These projects showed that nuclear rockets were not just a concept but a practical technology, achieving significant milestones such as full-scale ground tests and demonstrating engine performance that could meet the demands of deep space missions. However, the focus shifted away from nuclear propulsion with the end of the Apollo era and the changing political climate, largely due to concerns about safety, cost, and the anti-nuclear sentiment of the time. Today, advancements in reactor safety, materials science, and regulatory frameworks have addressed many of these historical concerns, making nuclear thermal propulsion a more viable and safer option. In recent years, NASA and other space agencies have revisited NTR technology. The urgency of sending humans to Mars and the need for advanced propulsion systems have sparked renewed interest. Nuclear thermal rockets promise to deliver the power needed for faster interplanetary voyages, and advancements in materials science and reactor technology, such as the development of high-temperature fuel elements and improved radiation shielding, have made them a safer and more practical option today. Of course, there are challenges to overcome. Political and public support is crucial for the success of any nuclear-based propulsion program, and transparency regarding safety measures will be key to gaining that support. Developing an NTR involves handling radioactive material, which raises concerns about launch safety and environmental impact. Advances in reactor shielding and safety protocols are being developed to mitigate these risks. For example, modern advancements such as composite materials for radiation shielding and autonomous safety shutdown systems are making NTRs significantly safer. If successfully developed, NTRs could revolutionize human space exploration by enabling missions to Mars, Jupiter's moons, or even beyond with greater efficiency and speed than current propulsion systems allow. Key benefits of NTRs include greater efficiency and specific impulse compared to chemical rockets, faster travel times, reducing astronaut exposure to radiation and microgravity, reduced propellant needs, making deep space missions more feasible. The potential of nuclear thermal rockets to open up the solar system makes them a compelling option for future space missions, ushering in a new era where long-duration human spaceflight becomes more practical. Are we witnessing the beginning of a return to these powerful propulsion systems? As we look toward ambitious space exploration goals, the answer may very well be yes. If you found this look into nuclear thermal rockets fascinating, don't forget to like, share, and subscribe for more in-depth explorations of the technologies shaping the future of space exploration.
Quantum thrusters are an exciting theoretical concept. Could vacuum fluctuations propel us through space? In quantum mechanics, even the emptiest vacuum isn't truly empty. It contains temporary particles that appear and disappear constantly. These quantum fluctuations represent the lowest possible energy state of a quantum field, sometimes called zero-point energy. The idea of harnessing or manipulating these fluctuations for propulsion forms the core of quantum thruster theory. The Casimir effect offers a glimpse into how quantum vacuum fluctuations might be harnessed. It describes a measurable force between two very closely placed uncharged metal plates, thought to be a result of quantum vacuum energy. The difference in vacuum energy on either side of these plates, caused by the restricted wavelengths of quantum fluctuations between the plates, creates an attractive force. Some researchers wonder if this effect could be scaled or manipulated to create thrust, perhaps allowing a spacecraft to be pushed without the need for traditional propellant. The EM drive, an experimental device claiming to produce thrust without propellant, generated interest by seemingly defying the laws of physics. Some speculated that it might somehow interact with quantum vacuum energy, as initial tests seemed to indicate small but measurable thrust. sparking excitement in the scientific community. However, repeated experiments failed to consistently replicate the claimed results, and the consensus so far is that it doesn't work as hoped. Still, it prompted many to dream about using quantum phenomena for propulsion, as it offers the possibility of achieving propulsion without propellant, potentially transforming space travel and making interstellar exploration more feasible. There are some major challenges to using quantum vacuum fluctuations for propulsion. Energy source. Quantum fluctuations are pervasive, but manipulating them requires precision and a method that remains hypothetical. Conservation of momentum. Conventional propulsion relies on Newton's third law. For every action, there's an equal and opposite reaction. A quantum thruster would need to exploit quantum vacuum fluctuations to generate a net force, potentially by creating an imbalance in the quantum field, without directly violating conservation of momentum. Scaling the effect. The forces observed in phenomena like the Casimir effect are minuscule. Developing a way to amplify these forces to a level useful for spacecraft propulsion is far from straightforward, as it involves overcoming challenges such as enhancing the strength of quantum fluctuations, precisely controlling the conditions to generate measurable thrust, and dealing with extreme energy requirements. If a technology like quantum thrusters could be realized, it would revolutionize space exploration. Propellant is the largest mass constraint in spacecraft design. Eliminating it could open the doors for deeper space missions, interstellar probes, and travel beyond the solar system's edge. Imagine voyages to rogue planets or distant stars without worrying about running out of fuel. For now, quantum thrusters are an intriguing but speculative dream. However, continued research into quantum mechanics and novel propulsion technologies is crucial, as it could lead to practical advancements in space exploration, enabling more efficient propulsion systems and making deep space travel more achievable. Still, our deepening understanding of quantum fields may someday lead to advances that make this idea a reality. After all, today's far-out theories could be tomorrow's everyday technologies. Exploring these boundary-pushing ideas inspires us to think beyond our limits, and maybe, just maybe, redefine what's possible. If you enjoyed this exploration of quantum thrusters, don't forget to like, share, and subscribe for more deep dives into the cutting-edge ideas shaping the future of space exploration.
Imagine embarking on an interstellar journey with no traditional fuel on board. Instead, your spaceship is propelled by the gentle push of light itself, using the momentum carried by photons to generate propulsion. This might sound like something out of science fiction, but the concept of laser-powered starships is gaining serious attention as a potential ticket to the stars. A new kind of journey. The idea is based on a deceptively simple principle. Use powerful laser beams to propel a spacecraft equipped with a lightweight sail, much like how wind propels a sailing ship. Unlike wind, however, lasers can maintain a consistent and focused push over vast distances, making them effective for interstellar travel where traditional propulsion methods would quickly lose power. This light sail captures the energy from the laser and uses the momentum to accelerate. Unlike conventional rockets, which are burdened by their fuel mass, a laser-powered starship could theoretically reach astonishing speeds because the energy source remains stationary, far from the ship itself. Breakthrough Starshot, a real-life example. One notable example of this approach is the Breakthrough Starshot initiative, which aims to send tiny, laser-driven probes to our nearest star system, Alpha Centauri. The concept involves ground-based lasers firing at ultralight sails, potentially accelerating them to up to 20% of the speed of light. At such speeds, the journey to Alpha Centauri, which would take tens of thousands of years with today's technology, could be completed in just a few decades. Imagine receiving images and data from a neighboring star system within a human lifetime, a prospect that would have seemed impossible just a few decades ago. The Breakthrough Starshot initiative envisions launching thousands of these tiny probes. Each probe will be equipped with cameras, sensors, and communication devices designed to send data over interstellar distances. These communication systems will rely on highly efficient transmitters and precise laser-based methods to ensure signals can reach Earth from light years away. By sending out a fleet instead of a single spacecraft, scientists hope to increase the chances of success. Even if some probes fail, others may make it, ensuring that valuable data is transmitted back to Earth. This concept highlights the resilience and adaptability needed for interstellar exploration. as well as the potential for collective achievement when many small, relatively inexpensive units are deployed together. The challenges ahead, however, there are challenges aplenty. The lasers need to be immensely powerful, requiring vast amounts of energy and sophisticated aiming systems to keep the beam precisely focused on the sail over vast distances. Any deviation could mean a loss of propulsion and mission failure. In addition to the need for precision, maintaining the coherence of the laser beam over many millions of kilometers presents a significant engineering challenge. Atmospheric disturbances and other environmental factors can disrupt the laser, which means ground-based installations may need adaptive optics, systems that compensate for atmospheric turbulence, or even space-based platforms to ensure the laser remains stable and effective. The sails themselves must be both incredibly lightweight and resilient enough to withstand the intense pressure of the laser beam without being destroyed. They must also be capable of maintaining their structural integrity as they are bombarded with photons at such high intensity. Advances in material science are crucial here, with researchers exploring options such as graphene, which is not only lightweight but also exceptionally strong. The sail's reflective properties must be optimized to maximize thrust while minimizing the risk of overheating or damage from the laser's energy. Navigating the hazards of space, and then there's the issue of navigating through interstellar dust, which could damage the craft traveling at such extreme speeds. Even tiny particles of dust can pose a significant threat when moving at a substantial fraction of the speed of light. A collision with a small piece of debris could potentially destroy the sail or the onboard electronics. Scientists are exploring ways to mitigate these risks, such as incorporating protective shielding or developing evasive maneuvers to dodge larger obstacles. One proposed solution involves using a forward-facing laser to vaporize small dust particles before they impact the craft, effectively creating a protective path through interstellar space. Moreover, communication with a laser-powered starship presents another significant challenge. At distances of several light-years, sending signals back to Earth becomes incredibly difficult due to the vast distances involved and the weak power available on such tiny probes. Researchers are investigating ways to use laser beams not only for propulsion but also for communication, allowing data to be transmitted over these immense distances with minimal power. The probes would need to be equipped with highly efficient transmitters and rely on Earth-based receiving stations with advanced optics capable of capturing these faint signals. The promise of laser-powered starships. Yet, despite these challenges, laser-powered starships offer an intriguing possibility for interstellar exploration. They represent a vision of the future where our reach is not limited by the amount of fuel we can carry, but by our ingenuity in harnessing the power of light itself. Imagine a network of laser-powered starships spreading across the galaxy, each carrying sensors and probes, sending back valuable information about distant star systems, planets, and even potential signs of life. This kind of exploration could pave the way for a deeper understanding of our place in the universe. Applications closer to home. The potential applications of this technology go beyond simply exploring other star systems. Laser-powered propulsion could enable rapid travel within our own solar system, allowing us to reach planets and moons in weeks instead of months or years. For example, missions to Mars could be significantly accelerated, enabling quicker human exploration and reducing the risks associated with long-duration space travel. Similarly, this technology could make studying the icy moons of Jupiter, such as Europa, more feasible, potentially advancing our search for extraterrestrial life. This capability could revolutionize space exploration, enabling more frequent missions to study the outer planets, their moons, and even objects in the Kuiper Belt and beyond. The technology could also be adapted for use in planetary defense, providing a means to quickly intercept and study potentially hazardous asteroids. A vision of the future. Perhaps one day, the sight of a shimmering light sail disappearing into the darkness will be humanity's first step towards the stars. It will be a symbol of our determination to explore, to push beyond the boundaries of what we know, and to embrace the challenges of interstellar travel with creativity and perseverance. The dream of reaching other star systems may no longer be confined to the pages of science fiction, but instead, it may become the next giant leap for humankind, a step that will open doors to incredible new discoveries and inspire future generations to look to the stars with hope and wonder. The spirit of exploration. The journey to the stars will not be easy, and there will undoubtedly be setbacks along the way. But the pursuit of such an ambitious goal is what defines us as a species. It is the drive to understand, to explore, and to expand our horizons that has taken us from the first steps on the moon to the edge of our solar system. laser-powered starships may be the next chapter in this story, a story of curiosity, innovation, and the unyielding desire to know what lies beyond. As we continue to develop the technologies needed for interstellar travel, we are also cultivating a sense of unity, a shared vision that transcends borders and generations, reminding us that we are all part of something much greater. One day, as we watch the light sail accelerate into the cosmos, we may realize that this journey is not just about reaching the stars, it is about understanding who we are and what we are capable of achieving together. The adventure of laser-powered starships is as much about the destination as it is about the spirit of exploration, the courage to face the unknown, and the hope that, somewhere out there, we will find answers to the questions that have driven us for millennia. With each new technological advancement, we move closer to making interstellar dreams a reality, proving that the sky is not the limit, it is just the beginning.
Imagine riding the cosmic winds, propelled by the invisible forces of our star. Magnetic sails, a futuristic concept for space travel, could make this a reality by harnessing the solar wind, streams of charged particles ejected by the sun that travel through space at high speeds, creating a constant flow of energy. These sails use magnetic fields to capture this energy, offering a vision of efficient, propellant-free space travel. With magnetic sails, we could traverse the vastness of space without traditional rocket engines, opening new possibilities for deep space exploration. Unlike rockets that rely on burning fuel, magnetic sails use superconducting loops to generate a magnetic field. This field interacts with the charged particles in the solar wind, creating electromagnetic drag to propel a spacecraft forward. The concept is similar to a sailboat catching the wind, except here, the spacecraft uses high-energy particles from the sun to generate thrust. By converting their kinetic energy into propulsion, magnetic sails allow a spacecraft to accelerate over time without needing propellant. Advantages of magnetic sails. Magnetic sails promise several advantages. They could provide continuous acceleration without carrying heavy fuel, making them ideal for long-duration missions. This continuous thrust could allow a spacecraft to reach significant speeds, enabling journeys to distant planets or even other star systems. Unlike solar sails, which require large reflective surfaces, magnetic sails rely on invisible magnetic fields, making them more versatile in navigating interstellar space. This flexibility could prove invaluable as we venture into regions where traditional propulsion struggles. Building on these advantages, one intriguing aspect of magnetic sails is their potential for interstellar travel. By taking advantage of the solar wind's energy, these spacecraft could maintain steady acceleration, covering vast distances more efficiently than conventional propulsion. This could be a game changer for missions aimed at exploring the outer planets, the Kuiper belt, or even neighboring star systems. The prospect of interstellar missions becomes more conceivable with magnetic sails, opening the possibility of finding new worlds and detecting extraterrestrial life. Challenges and hybrid solutions. However, the technology faces significant challenges. Developing lightweight superconductors that function at space temperatures remains a major hurdle. Superconductors are essential for generating the magnetic fields needed to interact with the solar wind, but current materials are often too heavy or require extremely low temperatures. Advances in material science are crucial for making this vision a reality. Additionally, maintaining superconductivity in harsh space conditions requires robust insulation and cooling mechanisms. The effectiveness of magnetic sails diminishes as the spacecraft moves farther from the sun, where the solar wind becomes less dense. This limitation affects mission planning, as it requires the use of hybrid propulsion systems to ensure continued acceleration and maneuverability in deep space. Magnetic sails are more effective for inner solar system travel but become less useful at greater distances. Combining magnetic sails with other propulsion methods, such as ion thrusters or laser propulsion, could help maintain acceleration even in weaker solar wind regions. Hybrid systems could extend the range and versatility of magnetic sail missions, ensuring spacecraft can continue their journey in deep space. A vision for the future. Despite these challenges, magnetic sails represent an exciting possibility for humanity's future exploration, a way to travel the cosmos by using the sun's energy. The development of magnetic sails could pave the way for new types of missions, from planetary exploration to deep space probes. By reducing our reliance on traditional propulsion, magnetic sails offer a more sustainable approach to space travel, ultimately enabling humanity to become a truly spacefaring civilization. Could magnetic sails be the key to interstellar travel? Only time, and further research, will tell. The promise of a propulsion system that harnesses the natural forces of our solar system is compelling. As we continue to push the boundaries of what is possible, magnetic sails may become essential for exploring the universe. The journey to making magnetic sails a reality is just beginning, but the potential rewards, a future where we explore distant worlds without traditional propulsion, make it a goal worth striving for. Moving forward, the future of magnetic sails depends on our ability to innovate and overcome technical challenges. Investments in superconducting materials and magnetic field generation will be critical. International collaboration could also accelerate progress, as pooling resources and expertise will help advance this technology. Magnetic sails represent a bold step forward, harnessing natural cosmic forces to explore the universe efficiently and sustainably. The promise of magnetic sails lies not only in their ability to propel us across the solar system but also in their potential to inspire a new era of innovation and discovery. Interstellar travel has long captivated humanity. With magnetic sails, we may finally have a technology that takes us beyond our solar system and into the vast unknown. Using the sun's energy to propel our spacecraft provides a glimpse of a future where space travel is not limited by massive fuel needs. As we explore and develop this technology, magnetic sails could become the foundation for a new age of exploration, one where humanity's reach extends to the farthest corners of the galaxy.